with this furnace so that you can use different rates. We call it as a T rates. You can heat your sample with 1 degree per minute. You can heat it with 5 degrees per minute or 10 degrees per minute. You can change the temperature as your wish, as per your wish, so that you can have programmable controller, temperature controller associated with this furnace. You have different heating environments. Air is there, you can pass air while heating your sample. So this is environment of the reaction. Secondly, you can use inert atmosphere, for example N2. Somebody uses argon, so mostly nitrogen is used, but if you are having too much money with you, you can have argon, which is more, we can say that inert gas. Okay. The temperature is normally increased at a constant rate. Constant rate means I will give, for example, if I don't have much data to gather from TGA, so this is the general rate, 10 degrees centigrade per minute heating will be there. So it means that initially my sample will be placed at 30 degree per minute, 30 degree. So after first minute it will reach to 40 degree, second minute it will achieve temperature of 50 degree, something like that. So you can have constant heating rate to induce the thermal reaction. The atmosphere within the furnace can be changed. So I have already mentioned air, nitrogen, something like this. So depending on the condition, for example, if you want to study the oxidation of metals or alloys, you can use air as a carrier gas, or you can use oxygen. If you don't want to have oxidation of your sample, you can use inert conditions. So you can have nitrogen that you can flush inside this furnace, and you can monitor the change in weight as a function of temperature. Okay. So you should know now, thermogravimetric analysis is something like that. We are changing temperature of our sample continuously. So we in temperature is under our control. So we are monitoring temperature. For example, if you are doing titration, so the solution that you take in burette is a standard solution. So you know its concentration and all those things. Likewise here, we know firmly the temperature of our sample. We don't know what will be the weight change. So what we have to do is that initially your weight of your sample will be, or we can say that it will be as it is. There will be no loss of your sample at room temperature or starting temperature. So we consider it as a whatever sample weight. For example, if you are taking 8 milligram sample for analysis, 8 mg sample for analysis, so you have to relate this 8 mg to 100%. So after reaction, this 8 mg will get reduced to maybe 4 mg or 5 mg or 2 mg, depending on chemical reaction. So if it is reaching to 4 mg, it will be automatically converted to 50%. So there will be 50% loss of your sample weight. So this is a relative, we can say that, quantity that we plot on the y-axis. So initial weight will be 100%. So sample if you will hit, so it will lose the weight, and if it is organic sample, you will reach zero at last, if it is organic in nature and volatile. But many inorganic samples are there which are not having, which are having some part volatile or decomposable, and rest of the part will be stable as a function of temperature. So what we study by using TGA? So we study decomposition reaction. For example, if you are taking any compound, if it is hydrated one, so water molecule, when you will heat the sample, water molecule will be removed from the structure. We call it as a dehydration process. So if your molecule is broken down in 2 or 3 parts, so it will be caused because of the breaking of chemical bonds or chemical association or physical association of molecule from the structure. So we can study the decomposition pathway of our sample. If only water is there, you can just monitor the evaporation process of your sample. The loss of volatile moieties at the increased temperature or higher temperature, you can study by using TGA. You can Study reduction processes by using TGA. Interaction of sample to a reducing atmosphere. For example, if you want to study the reduction of carbon dioxide, so what you have to do is that instead of nitrogen or air, you have to flush hydrogen along with that gas inside the furnace, so that this hydrogen will, uh, for example, hydrogen will react with your sample and it will reduce some of the elements in your sample, and that will be ultimately affecting the weight of sample. So here you will get some change in the weight if your sample will get reduced by hydrogen. So that kind of study you can carry by using TGA. Then desorption. For example, if A is there and on the surface of A, if B, small b is adsorbed, so you can heat your sample so that B will get removed from your A sample, so that only A will be there. So initially weight will be higher, after desorption rate will get decreased. So you can find out the concentration of B by using these particular desorption experiments. So in some cases, in TGA we can get weight gain. That is just because of absorption of another reactant in your sample, or if one of the element in your sample get oxidized, the weight will be increased. We will have some examples of this kind. So for oxidation you need to have oxidizing atmosphere in the furnace of thermal gravimetric analyzer. Okay, now we will not waste much of the time, so I will just take you to the interpretation of TGA of some of the inorganic compounds. You can use this same trick to analyze your data. If your sample is very straightforward, this trick will be applicable to each and every sample which has a defined or well defined decomposition pattern. So if your sample is a mixture of 2 3 compounds, then it will be little bit difficult to assign weight loss to any chemical reaction. Now you can see that our compound is calcium oxalate. What is the formula of calcium oxalate? CaC2O4 monohydrate. Means that if I will heat this calcium oxalate at higher temperature, first of all, this is a prediction. My theoretical prediction is that first of all, water will get lost from the structure. Water will get lost from the structure. In the second step, what will happen? So you will, if water get lost, I will have CaC2O4 in my hand. CaC2O4. These are the predictions plus water molecule. So it means that if I will heat my sample, in any sample, if you will heat it and if water is there, water will first of all get evaporated. So this first step in TGDTA of calcium oxalate, I will assign to loss of water. Loss of water. Okay, first of all, we will just see the probabilities and then we will make some calculations. This is water molecule is lost. You can see that molecular weight of calcium oxalate is 146.11. So if it has to lose water molecules, so how much mass it will lose? Minus 18. Water molecule has a molecular weight of 18, H2O. You can see that H2O. 2 is the atomic mass unit of 2 hydrogen and 16 is the atomic mass unit of oxygen. Now what you have to do is that you have to make this subtraction. So what will be the answer for this? Okay, we will do it here. 16, 8, 8, 3, 1, 2, 128.11 will be the remaining mass. So the mass carried forward here is 128.11. So all the molecules will get converted to calcium oxalate. You can see that temperature. What is the temperature here? So if this is 200, there will be 100 somewhere. So at 100 degree or more than 100 degree, So you know that boiling point of water is 100 degrees centigrade. If some weight loss is started near 100, you have to assign it to the water, loss of water molecule from the structure. So initially weight is 146.11. So now what will happen? Water molecule will get lost and this molecular weight will get changed to 128.11. So now there is one more step of the decomposition. Now we will assign that step. Sorry, you can see that. So now we can assign this step to one more reaction. This is another reaction. So there are total 3 steps in which this molecule get decomposed. Now we will see. Okay, we will come to this calculation little late. Now these are the theoretically predicted reactions. So this is a calcium oxalate monohydrate. When it is heated at 100 or more than 100 degrees centigrade, so it get converted to calcium oxalate. Water will get lost from the structure. In second step, calcium oxalate. This reaction we have to tell you, or we can build this reaction by going reverse from this. We can reach to this one and we can build this reaction. I will tell you in 1 or 2 minutes when we'll reach to the another slide. So these calcium oxalate further decompose to give you calcium carbonate and there will be loss of carbon monoxide. Now what is the molecular weight of carbon monoxide? Carbon is 12, oxygen is 16, so 28. So there will be loss of 28 atomic mass units. So here 28 atomic mass unit will be lost. So here your weight carried forward from the initial will be 100.11. 100.11. And in next step, there is a loss of carbon dioxide. Loss of carbon dioxide. So what is the molecular weight of carbon dioxide? It is 2 oxygen 32 and this one is 44. So you can reduce this, subtract this 44 from 100. So it will be 54.11 something. At the last, you will have 54.11% weight remaining of your sample. Okay. Okay, these are the prediction. We don't have to understand anything about it. We have to predict it theoretically, which reaction is like this. Okay. Now, first of all, we will see why we have to take this calcium oxalate as an example. So this is used in ceramic glazes for industrial applications. Secondly, this is a component of kidney stone in human being. So most of the time we can get these samples from industry as well as some health practitioners. And third, it is very important to calibrate the TGDT instrument itself. This calcium oxalate is used as standard. So it is mandatory for us to understand the thermal profile of this one. Now we can go to the data that we can get from the TGDTA. We cannot get any reaction. We cannot get any knowledge about these reactions by using TGDTA directly. We have to build these information from the calculation. Now I will tell you how to do it. So what we get in TGDTA? We get these particular weight losses. So what? 12.34. 12.34 is a weight loss in first step. Second weight loss is 18.7. So we will assign it and then I will tell you 18.7. And third weight loss is 30%. 30%. Or you can write 30.1 more simply. 30.09. 0.1 I will write. Okay, now what we have? So we know that our sample is containing calcium. Some organic group like oxalate is there. And there is some n molecules of water. We don't know initially. We have to analyze it. So when we prepare our sample, we know at least something. So what chemical we are adding in reaction bath? That is under our control. So if I am doing some preparation, so I myself is adding, taking a weight and adding those chemical component in my reaction bath. So no guest molecule from the planet will come and get included in your sample. So whatever we are making addition, that will only come in our sample. So if I am preparing calcium oxalate, so calcium will be coming, some oxalate will come. So I don't know what is the formula of oxalate, what is the content of oxalate in my compound, maybe 2 oxalate, 1 oxalate, that kind of thing. I also know that I am preparing my sample in aqueous medium, so water molecule will be there. So only this much knowledge I have. Now what I have to do is that I have to first understand that when I will hit any calcium compound having oxalate as a ligand, at last what I will get? Heating is nothing but the oxidation process. Heating is oxidation. So if your sample has oxygen, we will get at last metal oxide. What we will get? Metal oxide. Now it is our duty to find out the molecular weight of this calcium oxide. So now we will find out. Oh, calcium is having atomic mass unit of 40, and then oxygen is there, so 16. Total, how much will be the molecular weight of calcium oxide? 56. So what does it mean? When you heat your sample, so whatever remaining over there, so this end, so I will have in my hand 56% weight remaining with me. So there should be, how much weight loss should be there? Sorry, not 56%. Only 56 molecular weight I should have with me. If this is a 56, so now you can see that what you obtain? You obtain from TGDTA, first step 12.3%, second step 18.7%, third step 30.1%. Now you have to make this addition of these three. So 12.3 plus 18.7. So it will be 31. Addition of these two will be 31 plus this 30. So you will have total 60.1%. So 60.1% is a loss. 60.1% is loss. What is remaining weight? 39.9. 39.9. Now, if 39.9 is a percent weight, that is related to molecular weight of 56. Where from 56 comes? 56 comes that we assumed only stable metal oxide that can be formed after heating my sample is calcium oxide. If carbon oxide is there, carbon monoxide or dioxide, so that will be a gas that will get liberated into the atmosphere. So what I have to understand is that only calcium oxide is stable one and its molecular weight is 56, but that is corresponding to total 39.9% of weight of my original compound. So I have to find out the molecular weight of original compound. So how to do it now? So if 56 is considered as 39.9, we have to relate it. 56 atomic mass unit corresponds to 39.9. Then what will be the 100%? What will be the molecular weight of a compound when weight is 100%? So first of all, we have to find out the molecular weight. So how to do it? You can do it like this: 56 into 100 divided by 39.9. So you tell me now what is the answer. Yes, anybody Can tell what will be the answer at this stage? 56 into 100. So we can do it now. 5600 divided by 39.9. 140.3. 140. So first of all, I have to just tally this. Sorry, we can tally this. So you can just make 12.34 plus 18.7 plus this 30.1. Okay, 61.14 minus 100. So here something is wrong. It is not 39.9. So it will be 38.9. 38.9. So I made a mistake while making subtraction of 100 minus this one, 60.1. So if you subtract, here will be 61, sorry, this will be 61.1% because 12, 18. Here it is 30, it is 30, 60, and this point 0.3 and point 0.7 will have 1. So 61 lecture. So what you can do, uh, you can now change this as a 38.9. 38.9. Okay. Now if I have to get original weight of my sample, what you can do, 56 multiplied by 100 divided by 38.9, you get 144 somewhere around. What you get is a 144 somewhere around. Now you can see that 146.11 is the molecular weight of calcium oxalate. You can go into the literature or you can just build what is the weight of calcium oxalate, how many water molecule it can, you can attach it and then you can calculate the molecular weights. So it will fit, this will fit near to this calcium oxalate monohydrate. Now why there is a difference of 2 subunit? We have only considered the round figures here. So this molecular weight is there in which the exact atomic masses of this calcium, oxygen, carbon, hydrogen, everything is considered. Okay, now we understood that we have the initial compound which has molecular weight of 146. So 146 if it is, or 144 if it is the 100 molecular weight of 100% weight containing compound. Now we have to build a knowledge. For example, if this 144 will undergo a change of 12.34, change of weight by 12.34 weight. So how to accommodate it? You can consider this as 100%, then this is a 12.30%. So what you can do, if 144 correlates to 100, then what will be the molecular weight of a species related to this 12.3? Now I will write it something like this. 12.34, sorry, okay, this is 100%, so x. So you have, just a moment, okay. So what we have to do is that we have a weight 144 as a 100%. We consider, sorry, we consider 100% weight corresponding to the molecular weight of 144. Now what is the loss? First loss is 12.3. So you consider here, okay, 12.3. So what will be the molecular weight of species? Now how to do it? You just make a cross multiplication. 144 into 12.3. So that will give you the mass of the living species from your sample, 100. So you do it and tell me what will be the answer of this one. So we can do it. 12.3 into 144 divided by 100. So the most of the time, what will be the 17.7. So these are the rough calculation. If you will get the atomic masses from periodic table, it will be approximately equal to 18. Now you can consider the molecular weight of a species. We consider a species which has molecular weight of 18. Which species second step is something like this. We have to again use this kind of formula. Now initial weight is 100% weight is there, that can be assigned to a molecular weight of 144. Okay. Now how much is the loss? 19.2%. If 100% loss is there, molecular weight was 144. Now you have to find out if 19.2% loss is there, what will be the molecular weight of species? So it will be, you can multiply this 19.2 with this 144 and divide it by 100. So I will write it here. 144 into 19.2 and divided by 100. You can tell me the answer of this particular question. Okay, what will happen? 144 multiplied by 19.2 divided by 100. Exactly 27.6 is the answer. 27.6. So you can approximate it as 28, approximate to 28%. Okay. Now you can find out the species that has a molecular weight equal to 28. So you know from your chemical analysis, when you synthesize your sample, you will have chemical analysis by EDAX, by atomic absorption spectroscopy, as well as by doing some chemical methods or by having some ICP, X-ray fluorescence, something like that. So you know that in your sample calcium is there, carbon is there, oxygen is there, hydrogen is there. So now you have to have probability that which atom when combined with each other will give 28 as a molecular weight. So that will be exactly giving you carbon monoxide. So means we will relate the second step to carbon monoxide. Now there is a third step. In third step, there is a measured weight loss. You don't have to go to this side. So focus on this one. Measured weight loss is 30.09 in third step. Now you have to use this mathematics again. Now you can directly do it. 30.09. 30.09 or 1. You can write for simplicity. Multiply it with 144 and then divide it by 100, and just tell me how much is the molecular weight of the species that will be escaped at this step. So now we will do it. Okay, we can have 30.1 into 144 divided by 100. So exactly 44, approximately 44, 43.3 something is there. But this is just because the molecular weight we have not calculated accurate weight we didn't take. So it will be 44 somewhere around. So you have to find out a species which can have molecular weight of 44. So which elements are there? We have calcium, we have oxygen, we have hydrogen. So if you just combine it like this, CO2, because thermally carbon dioxide will leave. So it is having approximately weight of 44. So you can make this step because of decarboxylation of your sample. So that is why we have written. Now I will go to the next step. No. Now that is why I had written this. You can build up this reaction, decomposition reaction. So calcium oxalate is there. When I will heat it, so in first step, there is a loss of water from its molecule. So you can build the other reaction otherwise. You can have calcium oxide at last. Carbon dioxide is living in third step here. You can add these two together. So you will get calcium carbonate. So in the second step, calcium carbonate is there and there is a loss of carbon monoxide. You add calcium carbonate and carbon monoxide together, you will get calcium oxalate. In the first step, there is a water loss. So you can take calcium oxalate and then you add water. So you will get calcium oxalate monohydrate. So you can do vice versa. Either you can assume this and you can go to the bottom, or you can just, so this is logical. At last I will get only calcium oxide is a logical. This is just a trial and error. If you start from calcium oxalate monohydrate. So is this okay for you? So hello?
Yes,
Everybody
sir,
is
it's
convinced
okay.
with this, or I have to repeat it?
Yes, sir.
Okay, we will take more examples of this kind. Okay.
Hello. Sir, your screen is not visible, sir.
Yes, sir. Yes, ma'am.
Sir, your screen is not visible, sir.
Okay, you didn't understood.
नहीं सर स्क्रीन दिसत नाहीये सर
Screen.
स्क्रीन
Okay,
एक
okay. Oh, okay, okay. Okay, there is a problem in, okay, connection only. Okay, sorry. Okay. I think now visible. Okay.
now it is visible, sir.
Okay, okay. Okay, I will repeat it now.
Yes, sir.
Okay. So what we get from TGDTA, we get this kind of profiles. We get that initial weight is 100 and at last we get some weight is reduced. So what we have to do is that we have from profile, we have to get how much amount of weight is lost. So you just sum these three moieties of summation of this will give you. So you can just do the addition of these three 12.34 plus 18.7 plus 30.09. So you will get 61.13 weight is lost. So how much weight is remaining that you calculate. So subtract it from 100. So you will find that you have this weight remaining is 38.87. 38.87 means I will write it as 38.9% weight is remaining after heating the sample up to 800 centigrade. Now, at least when I will prepare a sample, I will know its origin or element present in it. Then and then only I will go for TGDTA. Okay. Now, I have to assign these three steps. So, which molecule is lost from this particular compound? I have to build up these reactions. These three reactions are built up from the calculation. Now, we will just initiate from 38.9% the weight remaining. So let me check the weight of calcium. Just a minute. Weight of calcium is 40.07, that is 40.1 you can write. So what I will understand, if I have any calcium compound with organic molecule, when I will heat it, finally I will get calcium oxide, because heating is oxidation. You have to keep in mind. unless until if it is not heated in inert atmosphere. Even in inert atmosphere, if your sample has oxygen, so that oxygen will combine with your metal. So at last we will get metal oxide, which is having a stable structure. So now I will find out the molecular weight of it. So there is addition you can do. 16 is the weight of water molecule, so you have 56.1 molecular weight. How much is the molecular weight of your final compound? 56.1. This is the atomic mass unit. That is molecular weight of calcium oxide is 56.1. Now if your residue that will have 38.9% weight. So what will be the molecular, this residue is there, we are assuming that it is calcium oxide and its molecular weight is 56.1. So then what will be the weight of my compound when it's 100%? Okay, weight was intact before heating. What will be the molecular weight of my compound? So if 38.9% is there, weight is molecular weight is 56.1. So what will be the weight for 100? So you just to do this calculations. 100 into 56.1 divided by 38.9. 38.9. Okay, make a calculation and tell me the answer. So this will be your molecular weight of this compound at initial stage. So you will do this calculation. 100 into 56.1 divided by 38.9. So 144.2 something is there. Actually, it should be 146.11. I don't know why it is coming like this. 144. Somewhere we have taken wrong things. Okay. Anyway, you can keep it in mind. We can approximate at last. So molecular weight of your compound is approximately 144 initially. So now you can just see first loss is 12.34%. First loss is 12.3%. So if this is 100%, if 144.2 is 100% weight of your compound, so how much weight will be corresponding to 12.34 loss? So you make cross calculation. 12.3 into 144.2. So answer will be something like this. Okay, we can do it once again. 12.34 into 144.2 divided by 100. 17.79 means 17.8 we will have, which is approximately equal to 18. Approximately equal to 18, that is a water molecule. So you can assign this loss to water molecule. So that is why we have removed water molecule in first step. In second step, the loss is related to 18.7%. Same calculation you can do. Instead of 12.34, now you use 18.7. So 18.7 into 144.2 divided by 100. It will be 27 somewhere around. Now 27, so we can approximate it to 28. So that is the weight of carbon monoxide. So some calculations are little bit deviated. So we can have this carbon monoxide loss. Similarly, you can just do it for 30.09. You will get 44 as a molecular weight. It will be CO2. So this is how you can analyze your TGDTA. So what is your observation? So in first step, water is lost from the structure, one molecule. In the second step, one molecule of carbon monoxide is lost. In third step, one molecule of carbon dioxide is lost. So this is how you have to make calculations. Otherwise, what you can do? You can do it in other way. Now we can use trial and error method. Now I will just make the same calculation in different way. Now initial weight is 100. Initial weight is 100. So you can assume that yours is calcium oxalate and its molecular weight is 146. You can find it on internet or on the chemical bottle. What is the molecular weight of this one? Okay. Now if 12.34% is loss in first step, what you can do? 100% weight corresponds to molecular weight of 146. So what will be the weight of 12.34% residue? You have to find it out. So what you can do? You can have 100. Sorry. Okay. It is not done here. Okay. You can just assume that first case, first step, water molecule is lost. So if 146 corresponds to the molecular weight of this one, and then if it is loses water molecule, so the weight will be reduced by 18. So you can do it by taking an example. If 100% weight is there, how much will be the loss? So if molecular weight is changing from 146 to, so 146 minus 18, that will be somewhere around 128. So one, after losing 18, what will happen? 146 minus 18, you will have 128. So then what will be there for 100? So you can do it 100 into 128. 100 into 128, you can take 100 into 128 divided by 146. So 100 into 128 divided by 146, if you do, you will get 87.7%. 87.7. So that will be corresponding to 12.3 weight loss. So these are the ways you can assign these weight losses, and you can build up the chemical reaction. Now we will go to next example. So this is a copper oxalate. Copper oxalate. When it is heated, it loses its weight approximately by, you can see that, 60, 40, some 47% weight loss is there, 47.5 weight loss is there when you heat copper oxalate at 300 degrees centigrade. Now you have to relate this particular weight loss to certain living species. So if you know the molecular weight of copper oxalate, molecular weight you can take from the bottle, or you can build it by adding the atomic weights of all the species. So if this is the starting weight 151.56, if it corresponds to 100%, so what will be the molecular weight initially? Okay, remaining, okay, I will write it as x for 47.5. So we can do it. So 47.5 is the loss. 47 point, sorry, it is not 47, it is a 50 here. 55, some 56, 57% loss is there. 56 or 57%. Okay. So now you can 57, we can take 57. So you can do 57 into 151.5 divided by 100. So I will do it. So 57 into 151.56 divided by 100 will be 86, somewhere around. Somewhere it is wrong. Okay, just a moment. 72. Okay, what we can assume is that after decomposition, it will give copper oxide. So there will be loss of carbon dioxide. There will be loss of carbon monoxide. So you have to find out the molecular weights of it. It is a 44, it is 28. So you just sum them up. 44 plus 28, it will be 72. 72 is the molecular weight loss from the original species. So if 151.56 related to 72, how will be the weight loss for 100.6? So 47% weight loss will be there for this one. Okay. Similarly, you can use any other compounds and you can build the reactions from this TGA profile. So this will be the example for you. So you can take it, this will be homework for you. You can take snap of this one, take a screenshot. So this is the profile and only you have knowledge about this particular formula. So you can build this reaction by doing the calculation at home. You can do it for the another compound. Okay. One more example here I just want to mention is a weight gain. Most of the time we define TGA weight loss. TGA as weight loss as a function of temperature. But some samples are there, they will not show the weight loss, but they will gain the weight. Here you can see that. Initial weight was 100%, but now the weight is 103%, something like this. Now you have different types of sample. You take an example of this green line, NiCr. This is over here. So what will happen? Some of the atoms on the surface, when you heat the metal at higher temperature, you can see the temperature is from where the metal gains weight. So it is more than 800. And what is the okay environment around your sample is oxygen gas. You are purposefully passing the oxygen in furnace of TGA and you are putting the alloy sample inside the furnace or inside the balance in the furnace. So the metal alloy will get oxidized, it will form oxide. So this is nickel chrome. So chromium is having atomic weight of 52. So when you heat chromium, it will form chromium oxide, Cr2O3. Plus 3 is a stable oxidation state for chromium initially. So it will form Cr2O3. Now if chromium, we have to relate this Cr2 to 1 chromium. So you just divide this by 2, you will have Cr1 O 1.5. For example, for 1 chromium which is having 52 its weight, you are getting after hitting Cr2O3, so that weight will be increased to 76. So you can just check how much percent weight gain is there by doing cross calculation. So there is a gain. Now, not all of the chromium atoms are getting oxidized. Only certain portion that is lying, certain chromium atoms which are on the surface of this alloy will get oxidized. So that your sample will get gain a weight during heating in the oxidative environment. Similarly, if you will get CRO formation initially, CRO, and finally it will get converted to Cr3O4, then also your sample will get weight, gain a weight, because oxygen per chromium atom, here it is one chromium atom, one oxygen is there, but after heating at higher temperature, so oxygen fraction in your molecule will get increased. Because of that, the oxygen will remain in your sample. Where from this oxygen is coming? This oxygen is coming from the oxidative environment that you are providing to your sample in TGA furnace. So oxygen will be added into your sample so that your sample will gain a weight. So this is the example that you can see uh, for the weight gain in TGA studies. And reason is that metal is oxidized. Initial oxidation state in alloy of chromium is 0. It will get oxidize to plus 3 so that it can have 1.5 oxygen atoms per atom of chromium. Then it can also go to higher oxidation state, or it can get reduced to Cr3O4. Some of the Cr will be 2 plus here and some of the Cr will be 3 plus. Out of 3, 2 will be 3 plus, 1 will be 1 plus. Then only this will have spinel formula. So you can explain the weight gain in TGA in this way. Now we will stop here for the TGA discussion. Now we will move towards the X-ray diffraction. We will get some examples. Now I will show you some of the examples in which we can calculate the crystallite size. So in XRD, most of the time, if you are writing a paper, just a moment, okay. When you are writing a paper, so your professor will ask you to enhance the data. So somebody will use Scherer equation and he or she will calculate the particle size, so called particle size or crystallite size, and they will include it into the paper. If they are preparing nanomaterial, so it is advantageous, or we can say that it will be appreciated by the referee if you will calculate this crystallite size and report it along with your particle size obtained by microscopy. Now what you can do, first of all, you have to clear yourself. So what is a crystallite size and what is a particle size? So crystallite size is different than the particle size. Particle is made up of several crystallites. You know bundi laddu, bundi ka laddu. So bundi ka laddu, one bundi will be crystallite and laddu will be a particle. Here we are mapping the size of this bundi, not the particle in XRD, because this is the zone in which all the grains are aligned repeatedly. There is no, we can say that, disturbance in the crystallite, so that you can have so many unit cell repeated in same manner. Okay, so what we analyze in crystallite size is in XRD by using Scherer equation is a crystallite size which is equal to the size of bundi in bundi ka laddu. So if your bundi ka laddu is made up of only one bundi, so we call it as a single crystal. We call it as a single crystal. If it is a nanoparticle of 10, 20 nanometer, it will show the broadening of the peaks. So there is, we can say that separate discussion is required why nanomaterials show you the broad peaks. So it is well explained in the BD Qualities book. If you are having a free time, you can download it from the internet. The name of the book is Elements of X-ray Diffraction. Elements of X-ray Diffraction. So Indian libraries, those are located in IIT Kanpur and Central University of Hyderabad has a right to circulate this book in the we can say digital form throughout the country. So you can Google it, you will find the PDF copy. So near around 124 or 114 page. So this Scherer equation is derived. So not many, we can say that, assumptions are there. So why this peak is broadened? You can only keep in mind that, so this Scherer equation is there that will help us to find out the crystallite size of our sample. Now what you have to do is that L is a crystallite size, or you can simply say now particle size for your sake of convenience. I never call it as a particle size. I always call it as a crystallite size. You can determine it by using this equation where K is a constant. K is constant, and for spherical particle, you have to check your ACM of your sample. It is 0.91 always for your sample which is having spherical particles. Lambda is the wavelength of the X-rays that you are using for diffraction experiment. Cos theta, here cos theta, theta is the angle. You are having 2 theta, you are having 2 theta. So what you have to do is that you have to divide that 2 theta by 2, you will get theta, and cos of that theta angle you have to use in this equation. What is beta here? Actually people write that beta is FWHM. It is wrong. So beta is not FWHM directly of your peak. So when you have X-ray diffractometer, so X-ray diffractometer will have its own contribution to the broadening of the peak. If we will take highly crystalline samples, very high crystallinity samples, if you will use for diffraction experiment, then and then also you will get some broadening to the peak. Then also you get some broadening to the peak. We call it as a instrumental broadening. What we call instrumental broadening. So what you have to do is that you have to correct this instrumental broadening from your peak width. Instrumental broadening. So now we will see how to correct this instrumental broadening. So what you have to do is that this beta is corrected FWHM. Beta is corrected FWHM. You when you write a paper, you can always mention that beta is corrected FWHM of your sample. So what is it? It is a square of square of b square. This is FWHM of the peak that you are considering, and the b small b is a FWHM of standard silicon you have to run on your instrument, and you have to find out how much is the broadening for silicon 111 peak. So generally this broadening is equal to 0.014 for many instruments. 0.014 angstrom. So this much, sorry, degree. So this much broad peaks you will get even your sample is highly crystalline. So this broadening is just because of instrument, and because of nanoparticle size your sample will show a broad peak. Now whatever broad peak your sample show, what you have to do is that you have to subtract the broadening because of instrument. So this is your capital B broadening. Full width means width from this side to that side at half maximum, means you have to find out the maximum and then you have to come half of its value, and then you have to take full width here. So now b minus b, so you have to make a square of b, then you have to make small b square, and you have to take under root of it, and that will become this beta. Now L is a crystallite size, K is a constant, lambda is the wavelength, beta is the corrected FWHM, and now cos theta. Now we will go to the second page. How to do it? So suppose that we can take an example in which somewhere it is mentioned that, okay, I will just show you some experiments have been conducted in which nickel nanoparticles are taken, and its first peak is observed 111 peak at 2 theta 44 degree. The radiation which we used is 1.542 angstrom unit, and this sample is not having any strain in it. Unstrained sample is there. Now whatever broadening of peak is there, that is just because of the particle size of it. So this FWHM is found to be 0.33 degree to theta. 0.33 degree to theta. Now what we have to do is that sample gave value of 0.3 for the instrumental broadening. Okay, now we have to, here somewhere it is not instrumental broadening, it is a broadening because of this particular nickel particle size. Now you have to calculate the L for it. So what you can do, you can just first of all take, calculate the beta. How to do it? So for this particular instrument, I got the value of 0.33. So you take square of it minus, for my instrument I know that broadening is 0.014. 0.014. You take a square of it. Subtract this instrumental broadening from my samples 1, then I will get beta is equal to under root. So 0.33 चा स्क्वेअर किती आहे बघा, 0.33 into 0.33, 0.33 into 0.33, it will be 1.1089, 1089, 1089 minus 0.014 चा स्क्वेअर, 0.014 into 0.014, it will be 000, one more 0, 196, 196. So this will not contribute a lot, but we have to do it. So this is the science that we can do by our own, so that our data will be non-ambiguous. Okay, what will be the answer? Square root of 0.1087. Now you take square root of it. So that will be your B. 0.1087 square root of it is something like this. Just a moment, let me do. Square root of it is 0.329. 0.329. 329. Okay. So this will be in degree. Now you go to the formula. L is equal to K. K you can write now 0.91. Lambda is in angstrom. You can see that lambda is in angstrom, 1.542. 542 angstrom. Now FWHM is angle. FWHM is angle. We have to convert it into radian. So we have to convert it into radian. Beta cos theta. Now your cos angle is 44. 2 theta is 44. You divide it by 2. So it will be 22. You cos of 22. So cos of 22 will be 22 cos. So it will be 0.927. 0.927. And here it will be somewhere 0.329. 0.329. Now what you can do? This is in degree. You have to convert it into radian if you want to have it in the linear scale. So now we can do it. So now we can make it something like this. So what is the conversion of degree to radian? Yes, degree to radian. Pi by 180. Formula for degree to radian is at pi by 180. So you will have to multiply it with 180 divided by, or you can simply multiply it with this one with 0.0175. You can just check it. Pi is 3.14 divided by 180. It will be 0.0. So here you have to multiply it with pi by 180. Pi by 180. 180. So that is 3.14 divided by 180, that will be 0.0174. So you can do it at last. 0.91 into 1.4, 0.91 into 1.542. It will be 1.40. I will write it approximately now. Divided by 0.329 into 0.927 into point not point not 175 or 4 you can take. So it will be 0.0005, 0.005. So this will be the denominator. Now whatever crystallite size that you will get will be in angstrom. So now you can do 1.4 divided by 0.005, 280 angstrom. So what will be the size of crystal light? That will be 280 angstrom. You know that 1 angstrom, 10 angstrom is equal to 1 nanometer. So this will be approximately equal to 28 nanometer, 28 nanometer, 28 nanometer. So this is the way you can calculate the crystallite size of your sample. Now we will move towards the ritual session because now time is we are lagging behind the time. Now I will share my window along with you. Stop sharing the screen. I will share the window. Share. Okay, window is there. Window is there. Okay, share the window. Okay. Hope everybody can see this demonstration. So PC GSAS or you have software called as a GSAS XPGV. GSAS XPGV. We can make folder here before starting anything. So we can give a name training PhD. Okay. You can download this GSAS and CPDW from website. Just Google it. It is free of cost. Can
Sir,
you?
screen is not visible, sir.
Oh, screen is not visible?
Yes, your window is not visible, sir.
Not visible. Oh, oh, oh. Okay, okay. Just a moment. We will just see it. I will just open some other thing.
Yes, sir.
Now it is visible. Oh, sorry. Sorry, sorry, sir. Wait, wait. Just a moment. Okay. TiO2. Is it visible now?
No, sir, no.
Oh, 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 there is a problem to this window. Okay. Anyway, we will okay use the PowerPoint only. So maybe okay. Okay. Share the screen, entire screen. Okay. Okay. I was not thought about. I didn't thought about this problem because I thought that window will be shared. Okay. Now what we will do? We will just have overview related to some samples. Okay. Just a moment. CW. Okay. I have some PDF. I will just show you CPDW. Okay. Is it visible, madam, now?
Yes, sir.
Okay. Okay. I will, what I will do, I will make some videos and then I will put it for the students. This is the manual that you can use for the ritual refinement of oxides by using GSAS software. This GSAS long form of GSAS is General System of Structure Analysis. So this software is generated by Los Alamos Laboratory, USA. So it is free of cost. Everybody can use it. So installing instructions are given here. So websites are provided. So you can just click any website on it. You can go to that particular server and you can download it. Downloading is very easy. Now after downloading, what you have to do is that you have to have your X-ray diffraction data with you. So I will just make one slide and I will type over there. So for ritual refinement, what is ritual refinement? Ritual refinement is theoretically you have to make a structure model. You have to simulate, you have to calculated XRD pattern of your sample, your structural model. You have to compare with your experimental X-ray diffraction pattern, point by point, and the difference should be less than 10%. So it is the theme of X-ray diffraction, sorry, ritual refinement. For ritual refinement, you need XRD data of your sample. Okay, I will just, okay. What do you need? XRD data. So XRD data that we get from the source or the instrument is in the XY format. So you will have 2 theta column, you will have intensity column. So what you have to do is that you have to copy this data from Excel, copy this from the Excel and paste it in Notepad. And then what you have to do is that you have to use another software called as Powder X. So this Powder X is the software that will convert any XRD data into 10 different types of files. So one of these file is compatible for GSAS. So you open that files in Powder X, or nowadays it is called as Convex. I will show you this Convex. Convex. So let me check whether we can. Okay. Convex. I will just to show you the software and where to convert the data. Convex. Can you, are you able to see the screen now?
Yes, sir.
Oh, okay. It is not compatible to show the direct demonstration of the software itself. Okay. Okay. I will just write the sequence. You have to convert the data that is obtained from the instrument into correct format. So if you are using full prop, you require .dat file. If you are using GSAS, you require .raw file. So all these XRD files can be generated by using Convex. You can write down this name, Convex. This is the software that can convert XRD data from one form to another format, which is compatible for any software. So for GSAS, you have raw data file GSAS, or you can convert the file into .gsa, either .raw or .gsa. This is your input that you require. Then you require instrument file .instr no .prm, parameter file, prm. It means that we have to give input to the software that which instrument we are using for the data collection, that will contain the value of copper K alpha, if it is alpha 1 or alpha. Then what you have to do is that you have to, in this particular instrument, the polarization of your instrument you have to give. So these files can be created by using GSAT itself, or you can use the files those are given in the examples of your software. So the third file you require is CIF, that is crystallographic information about your sample. Now I will just show you some slides where CIF is there. We have to go to this one application. Okay. Okay, what ritual does is that ritual is working on this formulas. So your intensity of your XRD pattern that is observed by you, and you have to make a model and you have to calculate the intensity of that peak, and then you have to subtract the intensity of calculated peak from the observed value, and then it should be less than this RF should be less than 10. So chi-square is not having any meaning if you are using powder data. So let me check whether I have some presentation on ritual. Okay. Okay, I think it is difficult for me now to show you the demonstrations directly for the ritual refinement. I will try to make a video by recording my screen, and then I will share the link with all of the students. Now we will stop here. If some students are having any queries, they can discuss it now. So before concluding my lecture, I should thank my mentors who have taught me the X-ray diffraction through my career. So my PhD guide, Dr. Vedarama Sami from NCL, right hand corner. She has made me, we can say, excel. She has excelled me in X-ray diffraction. I was enrolled for my PhD in catalysis. So she pressed me to get the PhD in X-ray crystallography. So after that, I joined the CNRS in Grenoble. So these three phases, so they are the, we can say that, experts in XRD. So they had given me a chance to work on synchrotron X-ray diffraction. So the interest about the X-ray crystallography has grown in my mind because of these three phases. This is Professor Eric Dury. Now he is in Brookhaven National Laboratory. This is Professor Jean-Louis Hodo. This is Professor Michel Anne. So they have taught me neutron diffraction, X-ray diffraction for the oxides and zeolites. This is Professor Hong, and this is Professor Kyungwan Nam, who were the mentors in Korea. So under the guidances of these phases, I could able to develop the, we can say, knowledge of X-ray diffraction throughout my career. So thank you for your patience. So I can share these slides with Professor Ahire sir,
Yes,
and I can make a video for the ritual refinement training.
yes, sir. Now the session is open for question answer. If you have any question, write down your question into chat box or raise your hand.
Yes. I think everybody understood everything. Otherwise, everybody understood nothing.
Yes, sir. Yes, sir.
Yeah, that may be the probability, either this or that.
Uh, so there is no question in chat box. I move to a vote of thanks for today's session. I would like to express my sincere gratitude to Dr. Dev Mangeswar for delivering an enlightening session on training for TGA profile interpretation and XID analysis. With his expert guidance and clear explanation, help us understand the subject effectively. We are truly thankful to Sir for this valuable contribution. Thank you so much, sir.
Thank
Uh,
you, ma'am. Thank you.
I would like to express my sincere gratitude to our college principal, Dr. B. A. Jagdale sir, course coordinator and head of the department, Professor P.B. Pawar sir, Dr. Andre sir, Dr. Vishnu sir. Thank you all chemistry staff members. Thank you everyone. Now the session is concluded.
Okay.
Thank
Thank you,
you,
ma'am.
sir.
Thank you.
Yes, sir. Thank you.